Thanks, Dong. Thanks, everybody, for attending. Let me describe briefly what we're going to do today, try to accomplish. First of all, this webinar is going to be discussing a new product release, which we think is highly innovative in a number of ways, and we'll take a look at that. It's called GCID. It's our version 3. It's been out for a couple of years, and we've been making continued progress and refining it and listening to our customers and developing new solutions. And the product is focused on GCMS qualitative analysis, identification of unknown compounds primarily, although the new version also has some capability for doing semi-quantitative analysis. So I'm going to try to run through a brief PowerPoint presentation to give you some background. And then I'll try to keep that reasonably short. And then after that, I'm going to actually show you some examples of the product in operation, some of its capabilities, and some of the things that you can do, which really you can't do in any other way besides using some of the approaches that we've taken. Okay, with that, we'll get started. Okay. So GCMS search has been around for a long time, and it's for qualitative analysis, identification of unknown compounds. It's really powerful, and the libraries have evolved, they've developed. But beyond that, there really hasn't been certainly the instrumentation's gotten a lot better, more reliable, more sensitive, but there really hasn't been a lot of progress other than that. And there's a couple of issues with GCMS search that sometimes people don't necessarily talk about. And the first one is when you're trying to identify an unknown and you do a library search, you get a library search hit list, which is a list of potential compounds that come from the library match algorithms. And these lists are not definitive. In other words, the top match in the list isn't necessarily the correct answer. So that's, and a lot of times people just say, oh, it's the computer's telling me that's the top match. It must be the correct answer. Well, that's not true. In fact, a lot of times that's not true. And there's a couple things that besides the fact that the library search is not necessarily definitive, there's other issues with the chromatography, and the primary one being the coelution of chromatographic peaks. If you get peaks, if you don't know they're mixture peaks, you're going to do a library search. You're going to get misleading matches, poor matches. You're not going to understand why. Is it because the compound's not in the library? Is it because it's a mixture peak? Do you have some background that's leaching from the column, some chemical noise? This is a big problem, and this is one of the biggest problems in GCMS. The other thing is this goes back to the fact that the library search is not a definitive hit list, is you really would like to have other metrics to help you give some confidence to what you're seeing in terms of the matches. And, good analytical practice really says that you should have a couple of other metrics at least to look at to help you pin down what the correct answer is. So everybody's probably seen this. This is a typical, a typical hit list, or it's basically the software goes and finds a peak. It does a library search. We by the way, we use the NIST search engine. So I'm going to talk about the NIST, when I say NIST hits and so on and so forth. We're using their algorithms. We like them a lot. And they also supply libraries too, but they actually have their application has an API, which we use to actually do the searches. So when you do a search, this is an example. This is a real example of what you might get. It's basically a hit list for a given compound. And the NIST search metrics, there's a number of ones you can look at. The one I'm looking at here is the similarity match. And basically, if it's 1,000, it's a perfect match. You never get 1,000. It's usually if you get something above 900, that's an excellent match. If you get something like around 850, high 800s, that's a good match. And we'll talk about why you might get these differences. And so this is your hit list for a given peak. And if you look at it, and this is an extreme case, but it's a real case, everybody's probably familiar with it. The top 18 matches are all 900 or better. So which is the correct hit? Well, a lot of people would say, well, it's got to be the top one. No, it's not necessarily the top one, because there's some variability in the MS measurement from instrument to instrument. Different manufacturers get slightly different intensity ratios. So the matches aren't necessarily at the top, aren't necessarily the best. And in fact, in this particular example, the third match is actually the correct one. But how would you know that? And how would you choose from those 18 ones? And that's the problem that we have. The other problem that I talked about is, of course, coelution. That's a big problem. So you have a peak. Here we have a peak at about 3.18, I believe. It's illustrated in this diagram over here. And so it looks like it could be pure. There's a little bump on the side here. Maybe it's a mixture peak. Not 100% pure. So what we do is of course, the software goes and takes that peak and does a search, and you get a hit list. Now, if you look at this hit list, you'll notice that the NIST match values are all pretty poor. 630 is a very poor match value. And it starts at the highest of 630. It goes down to 546. So it's like, what the heck, is it the compound just not in the library? Or is it a mixture peak and that's throwing me off base? Well, the reality is this happens to be a mixture peak. So if we have the ability to deconvolve that peak mathematically, and there's a lot of different ways to do that, what we can do is we can break that peak apart into its two pure component peaks, and hence its two pure component spectra, and we can search each of those spectra independently, and now we get some nice looking matches, and we know that there's two components in that peak. There's methyl isobutyl ketone, and there's another chlorinated compound in there. Notice here, though, however, for the second coeluting component, there's a lot of matches that are actually bunched up at the top here. These are all isomers. They all have the same formula, and the fragmentation pattern of the spectra look very similar. So it's very, very hard to discriminate. So we would like to have a better way to discriminate it, because we really can't do that by just search alone. So how do we improve the search confidence? Well, as I said, the first thing that we would like to do is identify mixture peaks. And we take a slightly different approach to deconvolution at Cerno. It's actually a two-step process. The first thing we do is we use something called principal components analysis, which is a statistical method of looking at a set of data, i.e. the spectra across a peak. And it enables us to, by looking at each spectra, it enables us to determine for a given peak if there's one or more components. Doesn't tell us what the spectra look like, but it's a first step process that tells us the number of components, and it's quite accurate. It's very reliable. Once we know the number of components, then we can try to back out the spectra by using more classic deconvolution techniques. We can also back out the background too, and we can do this all automatically, which is, you don't want to sit there. I'm sure people have played around doing background subtraction, trying to get it right. The goal here in this software is to automate all these things as much as possible. And so the advantage of our two-step approach is that we know how many components are in there, and other approaches tend to overfit. So you actually wind up fitting artificial spectra. So you may have a peak that only has two components, but the software may tell you there's 4 components in there, and a lot of them are just not real. So it's a nice kind of the other thing is there's not a lot of parameters to set. If you've ever used deconvolution software, you might have gone in and find out you have to tweak a bunch of stuff to get it to do the right thing. This pretty much eliminates most of that. Okay, so that's the mixture peak part. Now, how about the additional metrics? Well, one metric we could use is we can use the accurate mass formula identification as you would do in a high resolution instrument, to identify the molecular ion. If it exists, it doesn't always exist in all EI spectra, but it does in a good percentage of them. We can also look at the fragments, and that information can give us a clue as to whether the match from the mismatch makes sense. It also provides an additional benefit. If it's truly an unknown that's not in the library, it at least gives us some clue as to what the formula and what the actual structure might look like. The second one is retention index, and this is a really powerful tool. Retention index is truly orthogonal, and it's an extremely powerful tool, as we'll see as we move along. And again, we want to do this in an automated fashion. Okay, so retention index. The neat thing is that retention index databases are now really widely, they're rich, they're available. For example, the new NIST 2020 database, almost 100% of the compounds in the database have assigned retention index values. So this is a great tool for helping us, to help us figure out which is the right match from that NIST match list. It's an excellent orthogonal metric. And the interesting thing is it can be really good for distinguishing between isomers. And that's something that MS is not very good at. For example, if you get a series of isomers with the same formula, they're structurally can be different. You look at the EI spectra, they get pretty similar. So mass spec by itself is not a good differentiator. And of course, isomers can be critical, and they make all the difference in the world in terms of activity, whether they're toxic, whether they're non-toxic. And the other nice thing is that it's actually relatively easy to calibrate a GC with commercially available standards, like typically what's used is a series of N-alkanes. You don't have to use N-alkanes. You can actually use anything you want to do a calibration for retention index, as long as the peaks are spread across the chromatogram at a reasonably high density. And of course, in order to do this, you do need to make a separate run. That's sometimes not a big deal, but it is a barrier. And this is kind of feedback that we've gotten from our users, is like, we really like the retention index information, but we have to do an additional run. Sometimes it's a little bit problematic to get it set up right. It would be really nice if we could somehow do that magically. And so we thought about it a lot, and we've come up with what we think is a pretty revolutionary new approach, which we call Auto RI. And it does not require standards. And it allows you to get retention index information on any run. You don't have to have a separate retention index. You don't have to have internal standards. You can do it on data that you've acquired today, or you can use it on data that you acquired 10 years ago. We'll talk about how it works. It's kind of interesting, but it's really powerful, and it doesn't work in 100% of all cases. But as long as you have a reasonable number of identifiable compounds in your run, it works extremely well, a lot of times as good and sometimes better than using a standard like N-alkane calibration. Okay, let's talk about formula ID. Well, if you have an accurate mass instrument, you can get formula information, and you can use that to confirm your NIST match. That's a very powerful tool. And you can also do it on fragment ions too. And again, even if you don't have the compound in the library, if you get the fragment identification and the molecular ion, hopefully, you can get some ideas as to what the structure is. You can go to ChemSpider and look some things up, and at least start to get an idea. Even without MSMS, using EI, you can get a reasonable amount of information. And as I say, we can provide the formula fragment ID of compounds that are not in the library, which is in itself quite powerful. But of course, how do we do this on a quadrupole? And we have our workhorse GCMS instruments. They're single quad instruments, how do we get formula ID? And that's something that Cerno, actually, that's how our company got started, is by providing the ability to get formula identification from low resolution instruments. And it's actually relatively easy to do experimentally. What we do is we acquire the mass spec data in what's known as profile mode. We'll talk a little bit about that. And what we do is we perform something called a peak shape calibration on the spectral data. And what this allows us to do is it allows us to get very high mass accuracy, about 100 times better than a conventional uncalibrated quadrupole. And it also allows us to get something called spectral accuracy, which is our ability to model the ion profile. And again, we'll talk about that as we move along. But if we combine these two together, we have actually a very powerful identification machine, and we can do unknown formula ID. So just very briefly, I don't want to spend a lot of time on it, but when you acquire data on your instrument, this is a quadrupole resolving power about 800. This is typically what you'll see for a given ion. And so you have the A, you have A+1, A+2, A+3 here. So that's an ion, okay? And it's represented to you by the computer as sticks, or what we call centroids, okay? In reality, what's happening in your instrument is the detector is seeing a continuous stream of ions as it's scanning the quadrupole. So the instrument underneath actually acquires the data in what we call profile mode. Sometimes manufacturers also call it raw mode or continuum. So pretty much all quadrupole instruments can actually, you may not know it, but they can acquire data like this. And that's one of the requirements that we have in order to get formula identification. And why is it important? This is a series of compounds that are very close in mass, within a ppm. And even with a very high resolution instrument, you probably can't figure out which is the correct formula. This is LC, but don't worry about that. But if you look at the isotope profile, okay, and we could somehow model that exactly, and these are calculated spectra, of course, that's why they look so nice. But you can easily distinguish between these formulas by looking at that isotope profile information. And our ability to fit that profile information of the experimentally measured ion with a calculated ion, because we know the masses, we know the isotope distributions, that's called spectral accuracy. And so our ability, so we can use both mass accuracy, which is the position of the monoisotopic peak, and we can use this isotope profile information to nail the proper formula, the correct formula. So how do we do this? It's actually relatively simple. We acquire the data, as I mentioned, in profile mode. And then usually at the end of a run, it can be on a separate run, it can be at the end of a sample run. In your method, in modern instruments, you can say, turn on the PFTBA calibration gas. This is the gas that's used to tune the instrument. And we actually use it to develop our calibration from. So at the end of the run, the oven cools down for about 15 to 20 seconds, you turn on the gas. We can look at that and we can build this calibration, which gives us this high mass accuracy, high spectral accuracy. So using this, since we get a nice series of ions across the whole spectrum, we can use this to develop our calibration that corrects not only for mass error, but it also corrects what we call the instrument peak shape, the spectral peak shape, to a known mathematical function. This is really important because if we know the mathematical function of the peak shape, then we can easily compare it to calculated spectra using the same peak shape, just as I showed in the previous illustration. So what does that look like? Well, what we have here is three spectra, okay? Again, this is just one ion that we're looking at. The blue is an uncalibrated data. So that's what you get from your normal quadrupole GCMS. And this is real data. And so you'll see that it's not really a symmetrical peak. There's no defined function that you can really model this that well at. It's an arbitrary, non-mathematically undefined function. That's what you get out of all mass spectrometers, high or low resolution. So what we would like to do, though, as we talked about, we would like to compare the isotope profiles. But and what we see here in the red is actually a calculated isotope profile for this particular compound, C11H14O4. And if it matches up really well, that plus the mass accuracy is going to give us a confirmation of the formula. Pretty simple. Now, if I can take that calculated spectrum or the uncalibrated spectrum, and I use our calibration mechanism, we obtain the calibrated spectrum, which we now have calibrated to a known peak function. So we can use the calculated spectrum of the same peak function, and now we can overlay them and compare them very precisely. And this is actually real. And if you look at what we can do now, this is the formula, okay? The exact mass of that particular ion is 210.088. And the measured mass after our calibration is 210.093. So it's about 4.5 millidaltons off in mass accuracy. That's really good for a quadrupole. In the real world, this is obviously a really good example. In the real world, you'll typically see mass errors on a quadrupole of between 20 and 30 millidaltons. It's not as good as a TOF, but it's pretty good to start getting you there. But if we also compare the isotope patterns and use our spectral accuracy approach, we can compare the calculated with the calibrated, and we get here a spectral accuracy confirmation of 99.5. That means 99.5% of the information is explained by the calibrated spectrum when we compare it to the calculated spectrum. So that's how we can do accurate mass on a quadrupole. But it does require running in profile mode, and it does require, fortunately, very easily on a GCMS to turn on the calibration gas at some point. Usually a calibration will hold for a couple of days. So how does that work? How do we get 100 times better mass accuracy? Well, if you look at an uncalibrated spectrum, again, we're looking at the monoisotopic peak here. How do we find the center of that peak? Well, it's an asymmetric function. So really all we can do is we can look at the maximum perhaps, or maybe we can look at a few points around the top, and then we can estimate a mass position. And since the function is, since the quadrupole is not high resolution, that's a fairly broad peak shape. The accuracy that you'd get, manufacturers will quote you about a tenth of a Dalton. However, since we've calibrated now our spectra to a known peak shape, and we know what that function is, we don't have to just use 1 point or 2 or 3 points. We can actually fit the entire line shape or peak shape across that function because we've calibrated this to a known mathematical function. And that gives us a much more accurate, yes, we don't have high resolution, high resolving power, and the lines are broader, but we can still get a very accurate mass position. And we can get down to about the third decimal place. Again, about typically in real world, 20 to 30 millidaltons. But we've also, since we've calibrated the peak shape, we can also compare the calculated spectrum of a given formula from the mismatch, for example, and see how well it matches. But if we don't calibrate the spectrum to our known line shape, we can't fit it very well because we don't have a good, it's like comparing apples and oranges. And maybe we can explain 90% of the difference between these two lines. It's not good enough to do a formula identification. But after our calibration, you can see how well the calculated and the calibrated spectra match. So that's how we can do a formula identification. And this is where we got our start in the business. It's well-proven technology. There's hundreds of publications using it. It's actually an accepted method. If you're an organic chemist and you synthesize a compound and you submit it for journal publication, it's an acceptable technique. In addition to accurate mass instruments, you can use this approach to confirm the formula of what you've synthesized. So it's accepted by ACS, accepted by most journals. There's a nice article if you want to dig into the math analytical chemistry. It's actually available on our website that you can read about. Okay, so let's put it all together. So originally what we looked at in our match list is we looked at a single metric, which is our match value or our NIST match. And it went from in 900s being really good to, in the 800s, it's okay. And then when it gets below into the 700s, it's not very good. And we have a problem. But what we can do now is, and I'm just going to walk through these columns. This is a hit list for a compound. This is the NIST search. And we talked about it. If it's in the 900s, it's really good. So you can see the first three matches here are quite good. And I really can't say it's one or the other. I have to say it's one of those three compounds. There's something else I can do, and we'll talk about this in a little bit. It's called reverse search. It's actually a really powerful tool. Many of you may not know what it is, but it's a standard tool that's available in this. I'll talk a little bit about that in the next slide. And then this next column here that's basically our spectral accuracy match for the molecular ion. So what we do is for each hit in the hit table, we look at its formula and we calculate the spectrum, and then we match it to our calibrated spectrum. And if it's a very good match in the 99s, we have a super high confidence, again, just like an accurate mass machine, that we validated the formula. We can also look at the fragments and walk through the whole spectrum and determine the formula of the fragments. That's not as well differentiating as you can see, because there's a lot of common fragments between mass spectra. But we actually, if you want, you can actually go and look at the list of those fragments. And if it's really a true unknown, not in a library, it can again give you information to help you kind of back calculate what those probabilities are. Now, the next thing we look at is, we talked about this retention index and how powerful it is. So in the library, this RI-lib, that's the retention index for this compound here that's in the NIST library. So we read it out. It's in every entry has a retention index value. And we've calibrated our, using a alkane, for example, our particular chromatogram, and you can see that the difference between the calculated retention index and the library retention index it's off by about 45. Okay, so that's pretty far away. And we actually calculate another metric, which is just basically the difference between the calculated and the library retention index minus 100. So it's just an easy way to look at the data. So you know that if you look at RI fit, if it's 100, it matches the retention index perfectly. If it's 90, it's 10 units off. It's just a convenience unit. So if you look down the list here, you'll see that the RI fit for the top match is 54. And you'll notice that the software colors that, and this is what we do in the software, each line is colored as an indicator. And we call this magic highlighter. So what we do in the software is we can look at the NIST forward and reverse search values. And again, I'll talk a little bit more about that in a minute. We look at the conformation of the molecular ion if it exists. If it doesn't exist, we don't penalize it. We also look at the retention index value. And if the retention index value is far off, it's not the right hit. That's the nice thing about retention index, although you can get a lot of compounds that are reasonably close. So the software goes and looks at all these metrics, and it can decide how confident it is about which is the right answer. So if you look at the top match here, it's got really good search values. It's certainly that formula is correct, but the retention index is off. And if that's off, it's wrong, period. That's the way it is. So it highlights it as red. So that means that's probably not the right answer. And again, the second one, you can see the retention index, it's a little bit closer, but it's still off. It's off enough so that the algorithm goes and colors it red. But if you look at the third match here, you'll see that the retention index is really close. It's only off by about less than 6 IUs. And in addition, it also has very good search results, forward and reverse. The formula is correct. It's validating the formula. Notice these are all isomers. So what we've done here is now we have a tool that we can, well, your eyeball is the best, but we assist you with the computer to help you quickly identify, because you got to, normally you'd look through all this data, you try to, make sense of it. We let the computer do that for you and visually mark what it thinks is the right answer. So that really accelerates the review process. And if you look down here, you'll see this yellow one. What that means is that, okay, the retention index actually isn't that far off. 82 is not that far off, okay? But the search match is off, okay? So that's an indicator. But remember, it could still be a mixture. So you have to be a little bit careful. So therefore, it gets knocked down one unit, and it's a yellow. But then I go down here, and you'll see that this is interesting. This compound, it's got a lousy search in this, so it's certainly not the right compound. It's got a reasonable spectral accuracy, although it's not as good as the top match there. That's a confirmation of the formula. And but the mismatch is too far off, so it gets a yellow. Although notice that the retention index is pretty close. So that's another interesting piece of information. That also means that since these two retention indexes are close, beware, you might have a mixture. But because of the very good hit results here, I'm pretty confident that we don't. And by the way, deconvolution is not necessarily a perfect, is not perfect. For example, you cannot deconvolve two co-eluding components that are very close in time. It's just mathematically not possible. So it works sometimes, but it doesn't always work. So this is another mechanism that you can use. So what would you rather see? Would you rather just have these search values to evaluate your compound, or would you rather have all this information, and would you rather have it utilized by the computer to at least show you what it thinks is right? Obviously, you still need to look at it. I'd rather have this. So I'm just going to spend a little time, then I'm going to jump into a demo about forward and reverse search, because it's kind of important. Some of you may not be familiar with it. Forward search, it's very simple. What forward search does, it matches each peak in the unknown to each peak in the library. So if there's extra peaks, okay, in the unknown that aren't in the library, it penalizes the score. All right. So that means, for example, if you had a mixture peak, so it had more peaks in it than the pure component, you'd get a lousy forward search value. But if you look at the reverse search, it works kind of backwards, hence the name reverse. What we do is we match each peak in the library to each peak in the unknown. But if there are extra peaks in the unknown, we don't penalize it. So it's an indicator. If you look at their forward and reverse search, and their difference, and the forward search is lousy and the reverse search is very good. What that does is it means that it's likely a mixture peak. Okay. Okay. So let's. I'll put this slide up at the end. Let me start up the application, and I'll show you pretty much how it works. It's a very simple application. So this is GCID 3.0. It actually starts up with two windows. The main window here is, it's really a list processor. What the list processor does is it's just a list of the runs that I've processed. That's all it is. Very simple application. So these are all the things that I've been processing over the past days, and I'm going to walk through some of the ones at the top for this demo. This little window over here, that's basically when I process stuff, it's an informational thing that tells you what it's doing, and it logs all that information, and that gets associated with the run. So I can always go back and see if something went wrong or so on and so forth. So let's look at a typical run that I'm going to do. The first thing I'm going to do is I'm going to run an alkane standard, an external retention index standard. And at the end of that run, I'm going to turn on the calibration gas. It's going to run in profile mode data. And now I'm going to build a calibration from that. So if I go in and look at the how I set up the run, it's actually pretty simple. here, I just a note or comment, I describe what I'm doing. And then you'll see this, this field here says CGM calibration file. That's the alkane or other retention index calibration file. And you'll see here that it's called VOC accurate mass calibration. That's the name of the file. And at the end of that run, in the same run, I turned on the calibration gas. So in this next field, it says, where do you want me to go look for the spectral or the accurate mass calibration information, the PFTBA gas? And actually, I put it in the same file. So I just point it to the same file, and it knows to go and look for that particular gas in the file to do the calibration. And then finally, as a sanity check, I'm going to tell it, when you built the calibrations for accurate mass and for retention index, just analyze the alkane standard itself, just as a sanity check. And I can show you what this looks like when you process it. So I'm just going to say, I've already processed it. I'm just going to say reprocess it again. So I'll say reprocess it. I'll say go. If you look at this window over here, you'll see some text scrolling by. And let me go back and just show you what it did very, very briefly. It said it built a calibration file for the accurate mass. It found these peaks for alkanes, C5, C6, C7, at these locations. And that's what it's used to build the retention index. Then it went and analyzed the alkane itself, just as kind of a sanity check. And to go and look at what it did there and what the analysis looked like, I just double click on the run, and here's the analysis. So you can see the alkanes. This is my alkane calibration. And you can see that, again, this RI-lib value, that's the value of the retention index from the library. And by definition, C5H12, normal pentane, has a retention index of 500. And likewise, hexane 600. You'll notice that there's some impurities in here. It also identified those and actually identified them nice and correctly. So that's just a sanity check to make sure our calibration ran. So great. So we've done that. We've built the calibration. Now let's go and analyze our unknown. So what I do here in this next sample, let me show you what the setup looks like. Again, I make a note. I'm gonna analyze this. It's a VOC, simple sample. I'm gonna use an external retention index and accurate mass calibration. And I'm gonna analyze this data file right there, which is my sample. And this parameter file, okay, just kind of defines how everything works. And I'll talk very briefly about this. These are the parameters. Most of them you'll never touch. The things that are important is there's some here for chromatogram peak picking. There's something called instrument identifier here, and that basically tells the tells the system where to get the calibration files from. So that's basically the name that the calibration files take on after I've run the calibration. You choose which libraries you want to search. For example, here I've chose the NIST main and the NIST replica library. If I have Wiley libraries, these are Wiley libraries, I can search them. If you've imported a library, a user library from your instrument, or you built one in the NIST library, we can also include all of those in the search. Likewise, I say what kind of column I have for the retention index, and I also say what alkanes I'm using, C5 through C12. These are volatile. This is volatile, so I don't need to go that high. And this down here just lets me customize the reports. I can show anything I want. I can show cast numbers. I can show formulas, whatever you want. You can customize it to your heart's content. Okay, so that once that's run, I've already run the sample. I can go and look at the data and see what it looks like. So again, you'll see this. What we have here is this is the top level report. So for each peak, you'll see that it's got a retention time. It's got the NIST forward and NIST reverse search, as we talked about, the molecular ion validation, then the retention index information. You'll also see this column called mix. That allows us to, that's basically the software telling me whether it thought that particular peak was a mixture or not. So for example, if you see 1 out of 1 here, you'll see that's a pure peak. It's one, there's one component in there, and that's the first one. If there's more than that, for example, here we have 1 out of 3, 2 out of 3, 3. So in that peak at 1.5 there, it actually found 3 components, and then it tries to deconvolve them, and then it does the NIST search, and it does the formula identification and the retention index calculation. There's also a field called quant here. That's just, I can set up, the new version lets me do semi-quant. I'll talk a little bit about that at the end. If I didn't set it up, it just gives me the area in that field. So let's go look at a couple of examples here. Let's look at, let's zoom in here. And you can see here that we have marked areas. This is where we've co-added the spectra to obtain a spectrum for searching and for analyzing. And you'll see that the red bands indicate those are mixture bands, and you can see how many mixtures down here. And the blue bands mean that it just thinks it's a pure component. So for example, let's go look at this peak at 235. So I can just simply click at that. So again, this is just a high level table showing the best hit for each peak. Okay, but we know it's not necessarily always correct, and you can tell by, again, this color coding. So if I go in and look at this guy, you can see that the first component is that's been deconvolved here. The first match is very good, 977, 977 forward and reverse. That indicates it's pure. It's a good match. The molecular ion is correct. The retention index is quite good too, at 90. Okay, and it's basically the Z form of the isomer. And if you look at the next match, it's also really good. And so it's the third and the fourth and the fifth. But notice that I do have replicas. So I'm searching in the NIST library. They allow you to search replicas. And so it's actually valuable to look at those because they're slightly different measurements of the same compound. And since there's variation in the compounds, it's a good idea to look at the replica spectra. So you can see here that the next match is the E form, and it has a lower retention index fit. So I would say that's probably the right hit. Okay, this may not be as definitive of some of them, but that's actually a pretty good indicator, that along with the search metrics I'm getting here. So let's go and look at this peak up here at about 3.7. Again, another mixture peak. It looks like the first match, again, it looks correct. It's highlighted in blue. That means that it has good retention index. It has good forward and reverse. It's confirmed the molecular ion. You'll notice that these other ones are just the replica searches in the library. They're a little bit down on the NIST search, but they're all good. So I have a high degree of confidence that's the correct compound. Now, if I go to the next peak in the mixture, you'll see here that the retention, again, all good NIST search values. Obviously, they're the same formula, they're isomers. So that means the spectral accuracy doesn't really help us in this particular case. But the retention index value, as you can see, the top hit is 71. The next one is 93. So it wasn't color coded here because that doesn't quite meet the threshold. But 93, I have a high degree of confidence that we're looking at orthoxylene and not the 1,3-dimethylbenzene isomer. Okay, and then one more peak. Let's go back here and let's look at the peak at 1.8 here. Let's see, I think there's not there. 1.76, look at that guy. Okay, now here, this is interesting. We have very lousy NIST forward search value here. But the retention index is actually really good. And the confirmation of the molecular ion is good too. So what's going on here? If you notice, the forward search is lousy, but the reverse search is good. Remember what we talked about? The reverse search, it looks at the peaks matching into the unknown. So a high reverse search value is going to be somewhat immune to mixtures. So what that suggests to me is that that peak is actually a mixture. So the deconvolution didn't get it. But remember, you can't do deconvolution if the co-eluding species are right on top of one another. There's just no mathematical way to do it. But here, we've got some hints that, again, this may be the right hit. It's got the right retention index value. If I click on it and I overlay the NIST, see these bars, the NIST spectra is centroid data. So we put the bars and we overlay them on top of our accurate mass data. In addition, you'll see that you can look at the spectral accuracy match. You see that overlay there? That's the molecular ion at 78. And you can see how well it matches at 99.39% spectral accuracy, confirming that formula. But if I go back and I look at how the two library and the unknown line up, you can see like, oh my gosh, there's all these extra peaks here, here, and over here that are not in here that are not explained by just benzene. So now look down the RI fit column. Let's go find another compound that has a similar retention index. And if you go walk down here, you'll see that, and it's colored in yellow, even though the search value are poor, the retention index is good, and it's carbon tet. And if I click on it to overlay it, what do you see? Wow, that explains exactly what was not explained in benzene. So this is a very powerful tool, and you can actually figure out what is in mixtures without being able to deconvolve them. Because again, deconvolution does not always work. Okay. All right, so let's go and say that's great, but let's go back home again. And what I want to do is I'd like to do that experiment, but I don't want to I didn't run the retention index calibration. It was too much work, or it didn't work. So what do I do? Well, when I set up my run, all I do is I say, well, it's a profile mode spectra, so I can get accurate mass. So I tell it where to get the accurate mass calibration from, which is the same data file that actually the unknown was running. I just turned the gas on at the end, but there's no chromatogram there's no chromatogram calibration for this one. So what happens is that we automatically, when we do process that file, what we'll do is we'll automatically try to generate, using what I talked about at the beginning, a retention index value. So how the heck do we do that? And I'll show you the curve that we come up with and explain it a little bit. So what we do is we go through the run, we try to identify every compound. And again, remember, we can use the formula identification. We can use the forward and reverse search to make sure it's pure. And then we can plot all those out, and they should fit a nice smooth curve. If again, it's following a nice, so that's basically the time versus RI units. So we can actually generate a retention index curve from the actual compounds in the run. Now, obviously, if you don't have a lot of a reasonable number of identifiable compounds in the run, this will not work. But most of the time, you do have that situation. The next step that we do is, okay, remember that, okay, the search match may be very well, but the retention index may not match very well. So since we average and plot these on the curve, we can identify compounds that don't match the retention index trend, because you expect the retention index to increase monotomically. And so we can look at a compound that has a retention index value from the library that's more than 2 standard deviations away, and we can say, oh, that's an outlier. That's not the right answer. And so we can actually generate, and you see this little hook at the beginning here? That's real. You say, like, I didn't know retention index curves can look like that. Well, remember, we're using temperature programming. And in this particular run, we had an isothermal hold at the beginning. And if you remember your chemistry, isothermal modeling for retention index for an isothermal run is more logarithmic. And for temperature ramps, it's more linear. So that's why you get this bend at the beginning, because we have an isothermal hold. So it's real. So it's automatically generated retention index. And if you compare this to external retention index calibrations, it's pretty much the same. As long as you have enough data that's identifiable, you're going to get as good and sometimes better. And I'll show you the case where it's a little bit better. You'll notice that in the beginning, this is the same compound, I just haven't done in the external retention index. You'll see that the early samples actually have a better retention index match. That's because we take into account that isothermal bend. and it's not well taken into account when you just run a spaced alkane samples, because we have a lot more samples to generate a retention index curve. So let's go out here really quickly here, and so in actuality, this is better, a little bit better than external. If you look at this peak here at 6.18, okay, again, we have some really nice matches all bunched up at the top here, which is the right answer. Forward and search are all good. The formulas are good, but the retention index, again, is the breakout key. And you'll see here, the one that's blue, it's highlighted for me, is indeed the correct match for the compound. So this is an extremely powerful way to perform unknown IDs. Let's look at something a little bit more complicated. This is again, this is just the alkane calibration. Obviously, this is run like C8 octane through C26. So it's it's a longer run. Took longer to do it. You had to go through and run this external calibration. So you do that, and then you go and process. Now, this is an interesting sample. This is a sample of a plant material. We all know about making taking plants and making food that tastes like meat. So what you get in these particular compounds is you get a lot of terpenes. And terpenes, what that means is that you get a lot of formulas that are all exactly the same. So accurate mass doesn't help you all that much. So you really have to start to depend upon things like retention index to be the main differentiator for these particular compounds. Because as you can see, that this is again a top level list. Let's take a look at a compound here at 618. Let's see. Let's move down here. Oops. Nope, it's not what I want to look at. I want to look at 1021. So I want to look at this guy right there. So that's the hit list for 1021. And as you can see, there's a ton of isomers, and there's hundreds of isomers for this formula. And so how the heck do I differentiate and get the right one? Well, you'll see here at the top, there's this one, which is, again, all of these you need to consider as candidates from really at least the 12 all the way on up. You'll see that they all have good spectral accuracy matches, so that we know that's the formula. And the forward and reverse each match up. We know it's not a mixture. But the retention index is the only thing that's going to help us out for these kinds of compounds. And what you'll see here is you'll see, well, that's 91, that's 97. I don't have 100% confidence that that's the right one and not that one. It's got a little better NIST match values, but again, as we've seen, you can't really depend upon that. You have to consider all the good matches, but we can eliminate a lot of the compounds. And in fact, if you see the value 0 here, that means it's more than 100 IU units away. That means forget it, it's way out. So very quickly, I may not be able to nail it as the top match, but I can certainly say it's one of these compounds that is the correct match. All right, so the problem that with this method of running profile mode data, it's great if you're set up for it and that's what you're used to doing, if it fits into your workflow. Sometimes it doesn't fit into people's workflow, or they just want to have an additional tool to help validate and identify an unknown. And they've already run the data and they ran it in the classic centroid mode, because that's the way most people are going to run the data. So in the new version of the software, we support centroid mode data. So this is a centroid mode. If I go and look at the application, you can see all I have to do here, since there's no accurate mass calibration, no chromatogram calibration, I'm going to use the auto RA. I just process the data. So I can say, reprocess it here. Again, I'll reprocess it and it's going to go do it. You'll see the little window here. It's gone through all the peaks and it's identified them. It's done the search and it's done the retention index calibration using the auto RI. I can look at that auto RI curve. Looks pretty good. Looks really good. You can see the outlier there. And I click into it. And this is all generated by, I don't get accurate mass data, but I still get the retention index data. And I still get the other forward and reverse search data. So I look at peak 317. Again, it also does the deconvolution for me, even though it's centroid data. And so I can deconvolve this into two components. You see, this is the first of two. And I can go look at the next peak. Again, a bunch of isomers. I have to decide which one is which, and I can pretty much do that with the retention index. And kind of running out of time. I'm sorry, I went over a little bit. I hope this gives you a feeling. I didn't talk about quantitation. One of the things that we can do with quantitation, semi-quant, not full quantitation, but you can identify, you can define a target peak, and you can define a reference peak, and you basically do semi-quant with it by, you can take into account a scaling factor. But the interesting thing is we let you define these peaks by retention time or retention index. So that means that it can work a lot better. And we can also, even in a mixture peak, we can tell it to not only look for the retention time, but look for the component ID. So it's a very powerful mechanism. And with that, I'm sorry, we'll go and answer some questions, and Yongdong will handle that. Go ahead, Yongdong.
Thank you, Don, for the great walkthrough and the wonderful demo. If you could put up the last slides with additional information and context, we'll use that as a background to answer a couple questions that's coming in. Some of them came into the Q&A, some of them came through the chat. I will synthesize and combine them. The first question is that in the parameter setup in GCID, we use some notations for the column types.
Yes.
In terms of polar, semi-polar, and so on and so forth. How does that correspond to some other notations like DB1, DB5?
Yeah, we're using this tries to be vendor agnostic, so they don't use the more conventional names for the columns. But those column types, non-polar is basically DB1, if you're familiar with that. Obviously, there's trade names for that, and there's equivalent different variations of that. There's DB5, which is semi-non-polar, and that's probably the most common column people use. And then there's a polar, which is a wax column. So those are the three types of columns that there is data for. If you use something that's in between, unfortunately, you're out of luck. The good news is most people will use one of those three column types.
Thank you, Don. The other question is, do you have to use alkane in the case of external calibration, or you can use some other standard like SL ester?
You can use anything you want as a calibration for the retention index. I showed the alkane one. It's the most common one that people use. But for example, if you have a set of standards that you run as a validation set that you run every day, as long as you have peaks that kind of span the whole chromatogram, and the retention index of those, you have the option of going in and custom defining those compounds, and actually you just enter the retention index of them. So you don't need alkanes. You can use anything you want to calibrate, including the auto RI, which actually uses the data itself to calibrate.
Thank you, Don, for that. Next question, is it possible to customize the columns in the report, for example, adding the cast numbers to the peak hit list?
Oh yeah, the reports are totally customizable. I didn't really delve into that. I didn't have time. Unfortunately, I went a little over, but you can make PDF reports, and those columns that you see, those are fully customizable. You just go in. You might have seen the dialogue where it has a bunch of check boxes. You just go in and say, I want to see the cast number. I want to see the NIST ascension number. I want to see the molecular weight, the formula. I want to see the quantity. I want to see the area. I want to see the height. You can customize it for all those kinds of values to your heart's content.
Thanks, Don. Next question. Can this be used to identify novel unknown compounds that are not in the library?
That's a bigger challenge. If you think about it, when you do EI, I mean, think about MSMS when you're really trying to pick apart a structure. You can go and we can identify one problem is you really need to know what the molecular ion is, and you don't always get a molecular ion. So that the solution to that ideally is you run something like CI. So from that we can certainly identify the molecular ion, and then you can identify a bunch of the fragment ions. So you get a list of molecular ion, the formula, and you get the fragment ions. Then you can start to get some clues as to what the structure might be. But it's a tedious process, but that's what people have to do to identify real unknowns. And ultimately you wind up synthesizing the compound and seeing if it chromatographically is the same and spectrally. Yep.
Thank you, Don. Another question from the chat box. The PFTBA, does it have to be used after used in each injection, or
no? No. So yeah, the good question. Do you have to put the PFTBA in each injection? No. In fact, what we recommend people do is if you run, for example, an external alkane, put it in that one, and that's the only one you need to put it in. And the modern instruments are so darn stable. There's actually published work on this that the spectral calibration is good for many days. So at most once a day is all you need.
Right, thank you. The follow-on question is how long do you have to leave the PFTBA open?
15-30 seconds, Dong, would you say? That's probably.
Yeah, I agree. Another question that's coming in is that if you use the alkane ladder and somehow misidentified because you might have associated the wrong carbon number for the retention index calibration, do you have to reprocess the whole run after adjusting the ID?
Yes, you would. If you messed up on that's why I always kind of once I develop the external calibration, I run it against the alkane itself, and I validate visually that all the proper, because I know where the peaks are. So I make sure that it is properly located. That's what when it spits out that list in that window of where it found where it thought it found the different alkane peaks. That's really important, and I generally validate against that. So that's why one of the reasons that it can be a bit tedious to do an external alkane calibration. And once you get it nailed down, it's usually pretty easy as long as you're doing the same method. But again, with auto RI, that's why we did it, is because a lot of times it's tedious or the person just hadn't run it. And if you hadn't run it, and then 2 days later you've trimmed your column so your instrument, your GC, is not calibrated anymore. But with auto RA, it doesn't matter.
Thank you, Don. Another question: is it possible to provide a real data file for a more customized demo, and whether there's any difference working with data files from different vendors, such as the Shimadzu system?
Absolutely, you can do that. In fact, if you look at the red type there on the slide, it says, "Want to try it on your data?" We do this routinely. You're welcome to submit your data, and we'll process it for you. We're vendor agnostic. That's one of the things that differentiates us. So we'll work with Agilent. We can work with Shimadzu data. We can work with Thermo data. We can work with PerkinElmer GC data. It doesn't really matter.
Thank you, Don. And then last not least, is there a software IQ-QQ protocol for the GCID?
I'm sorry, what?
The question was, is there a software IQ and OQ protocol for the software? I guess it's a compliance testing
for publishing. We have our internal processes, so we don't have a formal external document for that.
Okay, we got the one extra question here. Acquisition in profile mode, is it a preferred or essential?
It depends. Again, it's nice to have that additional information. but it isn't always necessary. So if it's not necessary, and you really just want to, again, you saw what you could do with just using forward and reverse search, and what the computer can do as well, and using retention index data. That in itself is a big step up from just looking at a search. So that's why we support Centroid data as well. I would say that it's preferred, but if it's not convenient or it doesn't fit into your workflow, you're still going to get a big advantage in addition information for trying to ID unknowns.
Okay, so we're going to have take one last question, and then if you have any more questions, feel free to reach out to us through email or other means of contact. But we'll take one more question here in the chat box. If the deconvolution is not successful, I guess, is there can it somehow be complemented by those other mechanisms like a retention index and accurate mass?
You saw I did it. Well, first of all, I didn't show this, but we talked about a two-step deconvolution process. We run a PCA, and then, for example, let's say the PCA says there's 3 compounds in that peak. It then tries to deconvolve and pull out the spectra. It doesn't always work. Okay, it's just the nature of the math and the noise and the signal to noise and so on and so forth. If it, for example, cannot pull out the 3rd compound, it'll tell you that it found 3 compounds, but it could only find 2 spectra. Okay, so then I think your question is then can we go and do another level of deconvolution? For example, doing forward and reverse search. That's a great idea, and we've actually looked at that. I don't feel confident right now that we can do it reliably and automatically. But as you saw, it's quite easy to do when you review, because you can look at the data, you can see that this particular peak was not well identified because it's colored, and you go in there and you say, oh, and you have to go through that mental process to try to figure that out. So it's not automated. Hopefully one day it could be.
Thank you, Don. And with that, we want to thank all of you who come to the seminar today. I hope you find it useful and informational. As Don mentioned, you're welcome to submit data and contact us with any questions. I will be happy to work with you and your data. We have another webinar scheduled today, 6 hours later. If that works better for some of your colleagues, please feel free to ask them to sign up. Thank you all.